Hello, we're going to continue our discussion of momentum here. And so far we've discussed what momentum is. It's the combination of mass times velocity. It is a vector quantity, and it's just another way for us to describe the motion of an object. We discussed how interactions causes a change in this motion, right? An impulse causes a change in momentum. And then we're left with the question, well, why do we go through this process, right? We had force gives us acceleration with Newton's second law. We had conservation of energy. These both told us how do interactions cause changes in motion. So why do we create this new quality of momentum? And the reason why is because it provides us a very powerful tool called conservation of momentum that allows us to describe pretty complex interactions. And there are interactions that occur all the time, so it's useful to get familiar with these ideas. Now, for momentum, we're going to dive in a little bit, and in this video, we really only have one goal. We're going to explain what does it mean for momentum to be conserved. In future videos, we'll talk about the types of systems that are involved with momentum being conserved, and how to define those systems, because it is a very specific type of system. And notice I'm not saying object, I'm saying system. It is a very specific type of system that has momentum conserved. And then we're going to talk about how to apply this to different scenarios. But first, starting off, what is conservation of momentum? So momentum is really helpful for solving these complex problems we call collisions. When we have a collision, oftentimes we are talking about two objects that are heading towards each other and crash into each other, right? So we're going to imagine two cars here. They're about to get into a little fender bender, nothing too major. But they're heading towards each other with some initial velocity. I'm going to call car on the left 1, car on the 2 right. So we have V1 initial and V2 initial. Now, obviously, as they collide, they are both going to have changes in speed. And when they collide and they have their changes in speed, we can think about how can we determine what those speeds are, what can we predict those speeds to be. You might go to Newton's second law, F equals ma. And that was a wonderful tool if we knew what the force was. But here the problem is with a collision, and you've actually seen this behavior before in lab. If we were to look at the free body diagram for car 1, we would have, of course, the normal force going upwards, the weight going downwards, but you would also have here a force of car 2 on 1. And I'm using the notation here, F2 on 1, to be the force of car 2 acting on car 1. So the first thing in the subscript is the thing causing the force. The second thing is the thing feeling the force. So here, force 2 on 1. And if we were to look at this force on a graph, where we graph out the force 2, 1 versus time, if we were to look at this force, it would be something that peaks and then drops down. And again, you've seen this in lab when you've seen those acceleration curves and you've seen this like huge peak or this huge trough. This is the behavior that we see with a collision. And when we look at this, we see, well, this is very clearly a non-constant force. And it's a force that is non-constant and also that we can't really create a function for, right? We can't create a mathematical representation of this, not easily, to solve for Newton's second law using calculus. So there's not really an easy way to approach this with Newton's second law, so we say that's no good. We try maybe thinking about energy. Energy was a way we dealt with non-constant forces before. Maybe that'll help us here. But the problem is with energy, if we were to think about energy, well, energy is useful when it is conserved, when the total quantity of energy stays the same in a problem. But in this problem, we have some heat being created by the collision. If you ever feel a collision after the fact, it's going to be a little bit warm. Why is that? Well, that's because energy is being transferred into heat, which raises the temperature. We're going to talk a lot about heat next semester, but for right now, just know that it's a loss of energy, and it's a loss of energy we can't really quantify. So since we have that loss of energy to the environment that can't be quantified, well, energy's out the door. We can't really use it. So we ask, is there anything we can use? And the answer is absolutely. We can use momentum here. Momentum is really useful in these collision type problems because when we have, and I'm going to redraw my cars here real quick. I know my cars aren't the most artistically well rendered. But here we have car 1, car 2. They are heading towards each other. And we can use momentum here to analyze our objects. We're going to start off with the definitions, right? We're going to have some initial momentum before the collision. And our initial momentum is going to be m times v1 initial for car 1. And we're going to have the momentum of car 2 be initially mv2 initial. They're going to collide, and after they collide, they're going to have different velocities. Again, the collision causes them to change in their velocities. So we can likewise map out some final momentum, P1 final. The final momentum of car 1 is going to be mass of car 1 times v2 final. Again, vector, so I'll include vector arrows. And then we have P2 final equals M2V2 final. This should have been an M1 final. So we have our defined momentums. And this is just to say that there exist quantities of momentum here. Depending on what the masses are and the velocities are, we can figure out what that quantity is, but we're not getting bogged down by the specifics of what the momentum is, the actual value of it. We're just saying that it does exist. Okay, well, what can we do from here? The obvious thing to look for here is the change in momentum, right? We want to know how these things change their velocities as they go throughout their collision. So we would look at the change in momentum of 1. And what we learned in the last video is that the change in momentum is equal to the impulse that the car feels. So the change in momentum is equal to the impulse, which is going to be equal to final momentum minus initial momentum. And of course, all of these are vectors. That vector quality is going to be really important here in a minute. So here we have our change in momentum of 1. And of course, we have a change in momentum for 2, which is the exact same relationship, just swapping out the 1s for 2s. So we have our 2 momenta quantities and our 2 changes in momentum. That's really what we're going to be concerned with here, right? Because we want to know, how does the motion change? How does the interaction of our impulse cause a change in our motion? That's what we're concerned with. So we go a little bit further and we say, well, how can we define those interactions? We define those interactions by looking at the force that the objects feel and multiplying it by the time that they are experiencing those forces, right? So T here is the time of the collision. F is the force it feels. Well, for car 1, we would say that the force it feels is car 2 pushing on car 1. And for car 2, we have that the force is the force of car 1 pushing on car 2 multiplied by the collision time. So here we have our impulses defined by the forces they feel. But here's the kicker. Newton has 3 motional laws. And one of them says, his third law, says that the force that car 2 pushes on car 1 with, F21, must be equal to, in magnitude, the force of car 1 pushing on car 2 with the opposite direction. So I'm going to put a minus sign out there. And this is just to say that both cars push on each other equally hard in opposite directions. Car 2 pushes on car 1 to the left, and car 1 pushes on car 2 to the right. So with this in hand, we take our impulses and our impulses solve to tell us that our impulse on car 1 is going to equal negative the impulse on car 2. Since they have equal and opposite forces, they have equal and opposite impulses. The time is the same for both. That's just the time that the two cars are in contact. So that t is the same. The impulses are equal and opposite in direction. And when we take that into account, we are left with the idea that since the momentum changes according to the impulse, that the change in momentum 1, and I don't want to use red for that, the change in momentum for car 1 must equal the negative of the change in momentum of car 2. And this gives us a relationship here between the motion of the two cars that we can then link together. And how are we going to link them together? We're going to link them together by defining this new idea of a total momentum. A total momentum. The total momentum for a system is just defined to be the sum of the individual momenta that are present. Here, that'll be the momentum of car 1 plus the momentum of car 2. And we can say that P total initially is just P1 initial plus P2 initial. And we can define P total final to be P2 final plus P1 final. Doesn't matter the order we put it in. They're both going to be the same. So we have these total momenta defined by the sum of the individual momentas of our object. And what we've done here is we've combined our two cars into one system. So I drew this blue circle here, and that's to say everything inside that blue circle is our system that we're considering. So when we look for the total momentum, we're looking for the momentum of everything in our system. And here it is just those two cars, so we add their momenta together. And then we take this and we utilize some of the information we just found. Namely, that the change in momenta for car 1, well, that's P1 final minus P1 initial. Or we can rewrite this and say P1 final is equal to delta P1 plus P1 initial. And likewise, we have the same relationship for P2, our momenta for car 2. We find that P2 final is equal to delta P2 plus P2 initial. And if I weren't being lazy, I would include the vector arrows here, but I'm trying to keep things a little cleaner. And with these two pieces in hand, we are going to plug those into our P total final, and we'll get that our P total final is equal to P2 final. Well, that's going to be delta P2 plus P2 initial, plus our P1 final, which is delta P1 plus P1 initial. And earlier we found that delta P1 and delta P2, those are equal and opposite. Since they are equal and opposite, we can take these two delta P terms and say they're equal, opposite, they will cancel out, leaving us with P total final is equal to P2 initial plus P1 initial, which is exactly how we defined our initial momenta, which leads us to understand that the total initial momentum must equal the total final momentum for our objects, for our system. So we can't say that either object didn't change momentum. Both of our cars changed momentum, but what is true is that when we take both of the cars together, the sum of their momenta, whatever number that comes out to be, the sum of their momenta before the collision is the exact same as the sum of the momenta after the collision. And this here, this idea that the number that represents the quantity of momenta that's present, that number does not change over time. It does not change during the collision. It doesn't matter how complex our force was or the fact that energy was released. None of that mattered. Because in the end, it is true that the momentum doesn't change. And this is true so long as we say that we have a closed system. And we'll talk more about what exactly that means in the next video. We'll learn how to define these closed systems, how to then understand how to utilize those closed systems. All right, so this right here, this is the sort of derivation, the proof of conservation of momenta. In the next few videos, we're going to learn how to apply them. All right, I'll see you guys next time.